Vibration and Noise Control. Our team members are Pratik Kumar Oja, Rahul Malatu, and Kumar Sambhav. So the problem statement we are going to do is, we know that during seismic events such as earthquake, in tall buildings, bridges, and in many other structures, they have the tendency to move. Because of this movement in the building might have a catastrophic damages. So our project is an attempt to solve this problem by using the Toon mass damper technology. So basically, a tune mass damper is a mechanism installed in building or structure that aims to minimize mechanical vibration, and it typically involves a mass attached to one or more damper system. This mass can be made up of large concrete blocks or steel bodies, and when this mass is attached with a spring, it can be, we can also call it as harmonic absorber or seismic dampers. And the oscillating frequency of the tune mass damper is closely matches with the resonating frequency of the structure, in our case which is our building. And in seismic waves caused by the earthquake, which will make building move back and forth, and the movement may be back and forth, and sometimes it may also cause the building to twist at the top floors. So this earthquake can cause excessive damage to the construction and leads to the structure failures. So to enhance the building seismic performance, a proper building design is performed engaging various seismic vibration control technologies. Not only for the earthquake problem, but sometimes due to the a very large wind flow on, especially on the tall buildings on the top floor, this wind flow will make the building to move, which is not preferable in real life situation. So even in this case, we use Toon mass damper to tackle this problem. So now my friend Pratik Kumar Oja will take on with next slide.
Yeah, good evening, sir. So I will take you throughout the simulation part of the problem. We have made a simplistic model of the building, and we have used the software SolidWorks 2019 for that. The building consists of four columns and a slab, which can be supposed as a floor of a building. Uh, we have used the material of the building as AISI 120 steel, which is commonly used in building foundations. Next slide, please. And the frequency response of the simulation of the structure is studied in ANSYS 2020 software. Next slide. So initially, the structure, which is without the tuned mass damper, has been given an acceleration of 20 meter per second square. So why do we have given us acceleration, not a force? This is because we have kept in mind that for large forces, the acceleration of the system will decrease. So we have kept a constant acceleration, and the system has adapted the forces according to it. So this has ensured that the mass of the structure will not have any impact on the kinematics of the structure. So the next slide will depict the frequency response of the original structure. Next slide. As we can see from the next slide that the natural frequency, the maximum amplitude has been on the for the frequency of 30 hertz, which is 80.298 millimeters for the structure, which is a considerably large amplitude for a structure of that dimension. So next slide. We have concluded that the natural frequency of the structure is 30 hertz, and we have observed that the maximum amplitude of the structure is 80.298 millimeter. And this is an important point to note because our future interventions will help in reducing this amplitude only. So next slide. Uh, so the following is the rendered image of the tuned mass, the structure with the intervention of tuned mass damper. This structure is also made on SolidWorks 2019, and analysis is done on ANSYS 2020. Please, next slide. Next slide. So in this the pendulum as a tune mass damper is added. So we have done a few set of experiments with varied mass of the bob of the pendulum. For the pendulum, we have used the connecting link is made up of plastic, and the bob is made up of the same steel material which has been used for the column, that is AISI 120 steel. And we have also connected the link to the structure by a pin joint so that it freely has a one degree of freedom. And we have done this experiment for the height of for three different heights, for example 15 millimeter, 25 millimeter, and 35 millimeter. The length and width of the bob is taken to be 50 millimeter. Next slide.
Hello everyone, this is Sambhav Kumar. I'll be taking over for the experiments from now on. Given is a graphical analysis of our observations for a tuned mass damper of length 15 millimeter. The plot of amplitude versus frequency attains a peak at maxima of 30 Hz. The graph is a concave peak with higher slope modulo near the resonant or natural frequency. These graphs have been plotted using ANSYS 2020. Next slide, please. The same plot for a tuned mass damper of height 25 millimeter produces the following results. Firstly, the maximas can occur as well at other frequencies, but the global max again comes at 30 Hz, the natural frequency or the resonant frequency. The graph is again a concave peak near the maxima. Next slide, please. Similar results are obtained for the tuned mass damper of height 35 millimeters as well. The maxima comes at a natural frequency which is 30 Hz for this experiment. The graph is a concave peak. These are a clear indication of valid natural frequency of different structures. Next slide, please. As we can observe from the frequency responses of the three masses of the bob, there is a significant reduction in the amplitude of vibration using the mass damper. The best damping is shown by the bob of height 25 millimeters with an amplitude of 7.927 millimeters, the natural frequency. The amplitude has been reduced by 10 times. Our successive experiments also show damping. However, our best case of H is equal to 25 millimeters surpasses the others. Hence, the optimal mass as per this experiment is found out to be 0.49 kilograms. Next slide, please. We come to the conclusion that the tuned mass damper is an effective way to dampen out the seismic induced vibrations. It is a simple and efficient mechanism and shows lots of scope for further improvement. However, for large skyscrapers, there is an additional cost to design the mass damper, which increases the cost of investment. Overall, the mechanism can be implemented in different skyscrapers and different buildings as an effective earthquake deterrent mechanism. Thank you.